Okay, so if you're listening to this and you're a computer engineer, you're probably already dealing with big data in some way or another. But we're going to dive deep into big data service architecture in today's deep dive. It's not just about, like, giant data centers anymore, right? This stuff affects everything.
Yeah, absolutely. It's everywhere.
Like how cities are run, the apps on our
It's
phones.
true. Big data service architecture is like the backbone for how we handle these massive amounts of data, right?
Yeah.
Every second, more data.
Yeah.
And it's a complex system, think about it, with a lot of moving pieces, all designed to basically collect, store, process, analyze information, all to find those, like golden nuggets of insight.
So it's like building a nervous system, but digital for the whole planet. What kind of tech are we talking about to even make this happen?
It really is like a nervous system, you're right. And one of the most, I think, fascinating areas is on the data processing side. I mean, we're seeing a lot of breakthroughs in stream processing frameworks.
Okay, stream processing frameworks. So for people like me who don't deal with this every day, tell me more about that.
Basically, these are designed to handle data that's constantly flowing, like from sensors or financial markets where things are changing really, really fast.
Okay, so that's different from dealing with, like, static databases, right?
Hmm.
What makes stream processing so powerful?
It's all about speed and being able to react quickly. Take real-time fraud detection, right? So instead of waiting to analyze transactions in batches, with stream processing, you can spot anomalies instantly and react instantly.
Wow. So it's like having a security guard who's actually, like, watching everything in real time versus just reviewing security camera footage after something has already happened.
Yeah, that's a good way to put it.
What about the challenges in designing these systems? I mean, it sounds incredibly complex.
It definitely is. One of the biggest challenges we have is latency, especially when you're dealing with real-time applications.
Oh,
Every millisecond counts.
oh, I bet.
Researchers are constantly trying to optimize these frameworks to be able to handle massive data streams with like minimal delay.
So you're always racing against time, essentially, to make sure that that insight that you get is delivered fast enough to actually be useful. Okay, so we've got all this data, tons of it moving really, really fast.
Yeah.
How do we even keep it secured? I mean, we hear about data breaches all the time.
Right, right. And data security is, it's paramount, especially when you think about how much sensitive information these systems are handling, every day. One area I think is really interesting where there's a lot of innovation is in homomorphic encryption.
Homomorphic.
Yeah.
Say that again? Homomorphic.
Yeah, it's a mouthful, I know.
I'm adding that to my vocabulary list.
But basically what it means is that you can perform computations on data, but it stays encrypted. You don't ever have to decrypt it.
So give me an example of that. Like, how would that work in the real world?
Okay, so let's say you need to analyze medical records, right?
Mm-hmm.
Sensitive information.
Right.
Homomorphic encryption lets you do that while those records stay totally unreadable to anyone who doesn't have the key to decrypt them.
Wow. Okay, that's kind of like having a magic box or something. You get to
Mhm.
analyze the data, but you don't actually ever get to see it yourself.
Yeah.
That has to be a game changer for security, right?
Exactly. It's still a relatively new field, but researchers are making some very, very exciting progress. It has the potential to, I think, really revolutionize how we handle sensitive data, especially in these big systems.
That's really incredible. This is already blowing my mind a little, and we've only just gotten started.
Yeah.
Let's talk about where all this data is actually stored. I mean, it can't just be a few spreadsheets on your computer, right?
No, definitely not. Not anymore. We need really robust storage solutions that can scale, right,
Hmm.
to handle these massive data sets. So this is where distributed file systems, things like HDFS, Hadoop distributed file system, really come into play. They basically break up the data and then spread it across multiple servers.
So it's like having this giant interconnected warehouse, but it's all digital. And each server is holding a piece of the puzzle.
Yeah, you got it. And on top of that, you have things like NoSQL databases, which are really good at handling what we call unstructured data, things like social media posts, sensor readings. And these are designed for flexibility,
Yeah.
scalability, unlike, like you said, those traditional relational databases.
So it's about choosing the right tool for the job, right?
Yeah.
You've got different types of data, different volumes of data.
Yeah, exactly. And then you get into things like, okay, how do you divide up the data? How do you distribute it across all these servers to make sure that you're getting optimal performance?
So it's not even just about having the warehouse. It's about, like, figuring out the most efficient way to arrange everything inside of the warehouse so you can find what you need when you need it. What about, like, any emerging trends in how we're organizing and accessing all this data?
I think one really cool area is the use of graph databases.
Graph databases. Tell me more.
So these are really good at representing the relationships within data. So think about like social networks, right?
Ah, yeah.
Where it's not just about like a list of names and profiles. It's really the connections between people that matter just as much, if not more.
Right.
So graph databases allow you to capture those relationships and connections.
So instead of seeing a list of names, you're seeing like a map of who knows who and how they're all connected.
Exactly. And that's so valuable for things like, social network analysis, recommendation engines,
Yeah.
even fraud detection, being able to understand those complex relationships.
Wow. Okay, we've talked about processing data, how we keep it secure, how we store it. But what about making sense of all of it? That's where analysis comes in, right? Yeah.
Right, exactly. You've got all this data nicely organized, and now you've got to be able to extract those meaningful insights from it. That's where things like machine learning come into play.
Yeah, machine learning is really good at that, right? It helps us like unlock the hidden patterns, the trends, all the things that are kind of buried in this mountain of information that traditional data analysis, might miss.
So it's like we're training algorithms to sift through these like mountains of data and find those aha moments, those insights that lead to like, big business decisions, maybe scientific discoveries.
Absolutely, yeah. And one area where we're seeing a lot of innovation right now is deep learning, which uses these, get this, artificial neural networks.
Yeah.
And they're designed to like kind of analyze data in a way that almost mimics the human brain.
Okay, so deep learning, that's where things get really, really interesting because now we're not just talking about analyzing data, we're talking about like teaching these algorithms to recognize patterns on their own, to make connections and even start to make their own predictions.
Exactly, yeah. That's incredible. But what about the limitations? I mean, there have to be some limitations with this technology.
Yeah, so one challenge is that you need a ton of data, like a massive amount of data, and it has to be labeled to train these algorithms well. It's kind of like imagine teaching a kid to identify different objects. You've got to show them a bunch of examples before they can start to recognize those objects on their own, right?
Right.
It's the same thing.
So it's not even enough to just have a ton of data. It's got to be the right kind of data. It's got to be labeled. It's got to be categorized.
You got it.
So how are researchers dealing with that? Because it seems like a pretty big challenge to overcome.
It is. One promising area is something called transfer learning.
Transfer learning. Okay.
So basically, you train a model using a huge data set, I mean, massive data set for a general task. And then you take that model and you fine tune it for a more specific task using a smaller data set.
So it's like you're giving the algorithm a little bit of head start.
Exactly.
It doesn't have to start from scratch every time. It already has some knowledge to build upon. That's really cool. Where else, like in big data, are we seeing machine learning being applied?
Another big one is anomaly detection, finding those needles in a haystack, right?
Okay.
That's huge for stuff like, fraud prevention, network security, even something like predictive maintenance.
So I don't have to wait for something to break down or for some sort of fraudulent transaction to happen. These algorithms can look for those patterns and say, hey, something's off here.
Exactly. They're constantly analyzing patterns. They're learning what normal behavior looks like. And then anything that deviates from that norm, it's like red flag.
It's like a 247 security guard, but for all your data.
There you go.
That's awesome. So we've talked a lot about the technology, but what about the people who are building this stuff? What about computer engineers? Where do they fit in? Because it sounds like a pretty specialized skill set to build these kinds of systems.
Oh, for sure. Yeah. I mean, computer engineers are like essential to this whole big data ecosystem. They're the ones who are designing these systems, building them, maintaining them, making sure that they're scalable, reliable, and of course, secure.
So they're not just like, crunching numbers, writing algorithms. They're designing the whole like pipeline, the storage, the framework, everything that makes this all possible.
Totally.
What kind of skills are we talking about specifically that are in high demand in this world?
You've got to have a really strong foundation in distributed systems. Like you have to understand how to design a system that can handle these massive data sets that are spread across multiple servers.
So it's like being an architect, but instead of buildings, you're designing systems that can store and process information on this incredible scale.
Yeah, I like that analogy. That's a good one.
What about programming languages?
So you'll see a lot of Python, Java. Those are really popular for data analysis, machine learning, Scala as well, especially with Spark, it's a really powerful distributed processing framework.
So a good computer engineer, comfortable with these languages, understands these frameworks, distributed systems, I mean, they're ready to jump in and start working.
Oh, yeah. Don't forget about cloud computing.
Oh, right.
That's huge.
Of course.
Platforms like AWS, Azure, super important for deploying and managing all these big data solutions.
It seems like this is a field that is constantly, like, evolving. There's new tools, new technologies popping up all the time. What does that mean for the future of computer engineering as a whole?
I think, honestly, that big data is like transforming the entire field. I mean, the amount of data that we have, the complexity of it, it's only going to continue to grow, right?
Right.
So that means we're going to need more and more skilled professionals who can actually build these systems, manage them, secure them.
So it's not just about being, like, a code monkey anymore.
Mm.
You really have to understand the entire, like, life cycle of the data.
100%.
From how you're collecting it, how you're storing it, how you're processing it, how you're analyzing it. It's a lot.
Yeah, you got to be adaptable too, right?
Yeah.
Because like you said, it's constantly changing. You have to be a lifelong learner.
Always learning new things.
Always. Always. New skills, new technologies. It's just part of the job.
For any computer engineers out there listening right now who are like, this sounds really cool, I want to be a part of this, what advice would you give them? Like, what are some of the first steps they can take?
Honestly, the best thing you can do is make sure you have a really, really strong foundation in the fundamentals of computer science. Algorithms, data structures, distributed systems, those are key.
So it's like back to basics, but with this, like, eye towards the future of data.
Right, exactly.
What else can people do, computer engineers who are maybe listening to this? Like, what can they do to kind of prepare themselves, get ready for a career in this world?
I think get some hands-on experience,
Okay, yeah.
play around with some of the tools.
Like, what are some of the tools?
So, Hadoop, Spark, NoSQL databases. There's a ton of online courses, resources where you can, it's like a virtual sandbox. Play around, get your hands dirty.
Yeah, build those data castles, but, in the virtual world first.
Exactly, exactly. And then, honestly, don't underestimate the power of networking.
Oh, yeah. Networking is huge.
Go to conferences, join online communities, talk to people who are actually doing the work, day in and day out.
Learn from the best.
Yeah.
Okay, so we've talked about the technical skills, which are obviously really important. But what about the softer side of things?
Yeah.
Because I imagine you need to be, more than just a tech whiz to really thrive in this world.
Yeah, you got to be a good communicator.
Oh, communication is huge.
Hugely important. Being able to explain these complex technical concepts to people who don't live and breathe data.
Right. Because you might be talking to a CEO, a manager, who has no idea what a NoSQL database is, but they need to understand the insights that you're getting.
Exactly. Exactly.
What about problem solving? I mean, that's got to be up there as well.
Oh, for sure. I mean, big data is all about problem solving.
Right.
Taking these massive amounts of information, figuring out, okay, how do we solve this problem? So you got to be able to think critically. You've got to be able to break down complex problems into smaller, more manageable pieces. And then you got to be able to come up with creative solutions.
And that's where that foundation in computer science really comes into play.
100%, yeah.
Because it's about applying those core concepts to these real-world and very complex challenges.
Yeah, and, things change so fast in this field.
Yeah.
You've got to be adaptable. You've got to be a continuous learner.
Yeah, always learning.
Always.
So it sounds like a really challenging career path, but also incredibly rewarding.
Oh, absolutely.
Because you're always, like, at the edge of what's possible.
Yeah.
Pushing the boundaries with technology.
And every industry is being transformed by this,
That's what's so cool about it.
Healthcare, finance, transportation, entertainment, you name it.
So computer engineers out there, if you want to make a mark on the world, this is how you do it.
I agree. Big data is where it's at. It's such an exciting time to be working in this field. The possibilities really are endless.
Well, that is our deep dive into the world of big data service architecture. We've talked about the technology, what it is, how it works, and we've talked about what it means for you, for computer engineers, especially if you're thinking about, a career in this field.
It's been great talking about this. Such an important topic.
The one big takeaway, big data, it's more than just a buzzword, right? It is here to stay. It is changing everything, and there's a lot of opportunity out there for those who are ready to, like you said, dive in and get their hands dirty. Thanks for joining us today for this deep dive.